Hey fellow nerds, let us continue our discussion on Opamp applications. Today we will cover non-inverting precision half-wave rectifier, inverting precision half-wave rectifier, and precision full-wave rectifier. Let us start with non-inverting precision rectifier. But before we get into it, let's bring in the simple rectifier that we already know. This is a half-wave rectifier. We have a practical diode of knee voltage 0.7 volt. From the direction of the diode, we can see that the circuit will pass positive half cycle and it will stop the negative half cycles. But even when the input is positive, the diode needs 0.7 volt across it for it to be on. The transfer characteristics will look like this. It will only transfer positive input voltage that is greater than 0.7 volt. Instead of looking like this, the output will look like this. Now, what if the signal is so small that its amplitude is less than 0.7 volt? Then this circuit will not work. It will not pass any of the signal through it. So let us build a circuit using Opamp that will rectify even very small signals. A precision rectifier. We will start with the unity gain buffer. You know what this does? Nothing much. The output will be equal to input. Now, how does that help us? What we want is a half-wave rectifier. Let us say we want all the positive half cycle to pass through the circuit and all the negative half cycles to be stopped. That means for positive half cycle, V out should be equal to V in. For negative half cycle, output should be 0. Can we do it if we simply add a diode over here? Like this. Let us see how this works. We have two options. One is when the diode is off. In that case, the circuit will be open over here and there will be no connection between Y and V out. The circuit will look like this. Clearly, there is no feedback. Zero current will flow through R. Why? Because the only way some current can flow through R is through the terminal of the op-amp, which is not possible. So current through R is 0. That means potential across R is 0. Potential across R is our output. Output will be 0. In the second case, diode is on. Here Y will be directly connected to the output. The circuit will look like this. Clearly, we have a feedback. When there is a feedback, the op-amp will try its hardest to make sure the virtual ground condition is satisfied. That is, it will try its hardest to make the potential at these 2 points to be equal. Op-amp will adjust Vy, which is its output, so that Vx becomes equal to Vin. But Vx is equal to V out. So in this case, output will be equal to input. This is exactly what we wanted. But you might have a question in your mind. Even here, if the diode needs 0.7 volt to be switched on, how is the op-amp going to take care of it? That is exactly the question we will solve today. But before that, let me show you another way you can draw the same circuit. These are exactly the same circuit, just drawn a little bit different. Let us take the first case where input is 0. Input is 0 and we have a feedback. So the op-amp will try its best to make sure Vx is equal to Vin. For that, the only thing needed is that the diode should be on. For the diode to be on, it needs 0.7 volt over here. So the op-amp will increase the output Vy so that the diode is switched on and virtual ground condition is satisfied. Now, the diode is barely on. And in that case, we can model the circuit like this. I have replaced the diode with a 0.7 volt cell. Now, out of all the potential drop at Y, 0.7 will drop across the diode and the rest will come out as V output. This is Kirchhoff's voltage law. We can write V out is Vy minus 0.7. But why did the op-amp do this? So that Vx will be equal to Vin. Vin is 0, so V out will be 0. Which makes sense because the op-amp only has to increase the output Vy by 0.7 to barely switch on the diode. Here again you might have a question. When input is 0, then how can the op-amp make 0.7 volt here? The answer is very basic. The op-amp does not amplify the input. It amplifies the differential input. It amplifies V in minus Vx. Assume the op-amp has a gain 10,000. Then, to get 0.7 volt over here, what is the differential input voltage we need? It will be 0.7 divided by 10,000. That is 70 microvolt. It is a very small value. And there is something very basic that we learned in the first video of this lecture series. When virtual ground condition is satisfied, potential at this terminal and potential at this terminal are not equal. They are approximately equal. The difference between them is very small but not 0. 70 microvolt is a very small value. It is 0.00007. So that much difference between the inputs is enough for the op-amp to create 0.7 volt at the output. Isn't this exactly why we call it a precision rectifier? It can work with very small signals. Here, Vout and Vx are equal. When virtual ground condition is satisfied, these two potentials are approximately equal. Let us write they are equal. And input is 0, so all of these will be 0. Potential at point Y is 0.7 volt because the op-amp was trying to just switch on the diode. Let us take the second case where V input is negative. Since input is negative, we are giving a negative input to the positive terminal. So the op-amp output will be negative. We get a negative potential on the P side of the diode, which means the diode is off, no matter what. The circuit will break over here and it will look like this. Clearly, there is no feedback. If there is no feedback, the effective gain of the op-amp will be infinite. It's the original gain. Vin is negative, so Vy will be infinite gain multiplied by some negative value. But obviously Vy cannot be negative infinity. It will stay at minus Vsat, the saturation voltage. Now, how about the output? No current will flow through the resistance R. Why? Because the only path through which a current can flow through R is this. That means current should come out of the input terminal, which is not possible because for an ideal op-amp, input impedance is infinite. So no current will flow through R. Vout basically is the potential drop across R. Since there is no current in it, Vout will be 0. Let's take the third case where input is greater than 0. We are giving a positive input for the positive terminal. At Y we'll get a positive value, diode will be switched on. Now, again, there is this thing that op-amp does, right? Op-amp will try its hardest to make sure that the potential here is equal to the potential here. We know out of whatever potential we have at Y, 0.7 will be dropped over the diode. The rest will come out over here. And the op-amp wants this to be equal to this. So at Y, op-amp will give V in plus 0.7. So that even after 0.7 drops across the diode, we'll have V in here. Potential at X will be equal to potential over here. So this is what the op-amp does. It will raise the potential at Y to that point so that when current finally flows through R like this, it will be enough to make the potential across R equal to V in. Because potential across R is finally what is output. And that is exactly what Vx is. So if potential across R becomes V in, V out becomes V in, Vx becomes V in, Vx becomes equal to the potential over here and virtual ground condition is satisfied. Ultimately, that is what the op-amp wants. Let's write this down. Op-amp raises Vy more so that the current flows through R and Vout, which is equal to Vx, becomes finally equal to V in. Virtual ground condition is satisfied. diode will be on and the circuit will look like this. I have replaced the diode with a 0.7 volt cell. Again, V out is equal to Vx and it will be equal to V in. And one thing we have seen is that V in doesn't have to be a large value for Vy to be enough to switch on the diode. Even a very small potential difference between these 2 points is enough for the op-amp to create a potential over here that will switch on the diode. Why? Because the op-amp has a really high gain. We just saw that. Even when input was 0, the op-amp was able to switch on the diode. So we can write, even for small positive inputs, V out will be equal to V in. The op-amp will try everything it can to make Vx equal to V in. But then Vx is also equal to V out. And what is V out? According to Kirchhoff's voltage law, it is Vy minus 0.7. So we can write V in is equal to Vx and that is equal to Vy minus 0.7. Then Vy is V in plus 0.7, which makes sense because the op-amp wants V in to be here, but 0.7 will be dropped over here. So at Y it will give V in plus 0.7, so that even after 0.7 is dropped across the diode, we still get V in at the output. Let's take all we have at one place. When V in is 0, V out is 0, Vy is 0.7 volt. When V in is negative, V out is 0, Vy is negative Vsat. When V in is greater than 0, V out is equal to V input and Vy is V input plus 0.7. Let's try to plot all these. We'll take a sinusoidal input signal like this. The final output will be like this. For negative half cycles, it is 0. For positive half cycles, it is equal to input. Let us also plot Vy. For negative half cycles, Vy will be minus Vsat. For positive half cycles, it will be input plus 0.7. When input is 0, it is 0.7 volt. The graph will look like this. Let us also plot the current through our diode. A current will flow like this through the diode and it will flow through R. Because obviously current cannot flow into the terminal. Let's call the current I. When input is positive, V out is equal to V input. But V out is the potential drop across R. R has V out here and 0 here, so the potential drop is V out minus 0. Then the current through R will be V out divided by R, which will also be equal to the diode current. When input is negative, output is 0. That means potential across the resistor is 0, current through it is 0, which is equal to the diode current, so diode current is also 0. If we plot it, this is how it will look like. Now, what if I want a non-inverting precision rectifier that rectifies all the positive half cycles and keep the negative half cycles? Well, it's very simple, isn't it? All we have to do is change the direction of our diode. Make the circuit look like this. Let's see what happens when input is 0. Like we saw earlier, the op-amp will try its hardest so that Vx will become equal to V in. But for that, we need a feedback loop. Op-amp will try its best to make a feedback loop by switching on the diode. To switch on the diode, it needs to give negative 0.7 volt over here. So op-amp will make the output negative 0.7 volt so that the diode is on and Vx becomes equal to V in. Since V in is 0, Vx only has to become 0 volt. That means the op-amp only has to provide a negative 0.7 volt so that the feedback loop is there and the potential here will be 0. Vy will be negative 0.7 volt. And all of that will be dropped across the diode. At output, we will get 0, which is also equal to potential at X. Since input is 0, this will be equal to the potential at this terminal and op-amp is happy. Virtual ground condition is satisfied. So when V in is 0, Vy is negative 0.7 volt and output is 0. Now, what happens when input is negative? We are giving a negative input to the positive terminal. So output will be negative which means the diode will be switched on. Whatever is the potential drop we have at Y, out of that negative 0.7 will be dropped across the diode and the rest will come out over here. But the op-amp wants whatever we get here to be equal to V in. So it will give V in plus an extra negative 0.7 at Y, so that even when negative 0.7 is dropped across the diode, we'll still have V in here. That means Vy will be V in plus a negative 0.7 and V out will be equal to V in. We have already seen that even when input is very small, the op-amp will still be able to produce enough potential at Y. And that is exactly why we call this a precision rectifier. Let's take the third case. Input is greater than 0 volt. Input is positive. If input is positive and we give it to the positive terminal, at Y we'll get a positive value. However much the value is, the diode will be switched off. If the diode is switched off, there will be no feedback. With no feedback, the effective gain is the original gain, which is infinite. A positive input multiplied by infinite gain will give positive saturation voltage at Y. Vy will be plus Vsat. How about output? No current will flow through R. That means no potential drops across R. That means V out is 0. Let's try to plot this on a graph. We'll start with a sinusoidal input signal. The output will look like this. It has all the negative half cycles. Positive half cycles are rectified. Let's plot Vy also. When input is 0, Vy is negative 0.7. When input is negative, Vy is input minus 0.7. When input is positive, Vy is positive saturation voltage. The graph will look like this. How about we also plot the current through our diode? A current will flow through R in this direction and then it will flow through the diode. It's in the opposite direction because the diode now is in the opposite direction. Current flows from P to N side of the diode. Now, when input is positive, output is 0, which means resistor has 0 potential across it. Current through it will be 0, but it is the same current that flows through the diode, so current through diode is also 0. When input is negative, output is equal to input. Resistor will have 0 potential here and V in here. So the current through it will be 0 minus V in divided by R, or negative V out by R. If we plot it on a graph, this is how it will look like. For the negative half cycles, output is negative. That is why negative V out by R becomes positive. Current is positive because we took the right direction. Let us now build an inverting precision rectifier. Instead of giving the input at the positive terminal, we will give it at the negative terminal. The circuit will look like this. Input is given through resistance R to the negative terminal. We still have a negative feedback through the diode. Output is still taken at X. Positive terminal is grounded. Let's take the first case where input is 0. When input is 0, the op-amp will try its hardest to make sure Vx is equal to 0. But then for op-amp to be able to do that, there should be a feedback loop. For the feedback loop to exist, diode should be on. For the diode to be on, it needs a negative 0.7 volt over here. So op-amp will raise Vy to negative 0.7 so that the diode is on, so that there is a feedback loop that will help it make Vx to be equal to 0. Basically, to satisfy virtual ground condition. When this is done, the diode will be barely on. Then the circuit can be modeled like this. I have replaced the diode with a 0.7 volt cell. Now, Vy is negative 0.7. All of that will be dropped across the diode. So at output, we have 0. That means at X, we have 0. Potential here is equal to potential here, and virtual ground condition is satisfied. Applying Kirchhoff's voltage law, we can see that V out will be Vy plus 0.7 volt. But since Vy is negative 0.7 volt, like we said, V out is 0. That means V out, which is equal to Vx, will be equal to the input, which is 0. And Vy at this point is negative 0.7 volt. Let's take the second case where input is negative. When input is negative, the diode will get a negative potential on its P side and it will be switched off. That means the circuit will be broken over here, and we can model it like this. Clearly, there is no feedback loop, which means the effective gain is the original gain of the op-amp, which is infinite. We are giving a negative potential to the negative terminal. So output should be negative infinity multiplied by some negative value, which will make the output plus saturation voltage. Vy is plus Vsat. How about V out? No current flows through R, because if current flows through R, then it will have to go into the terminal, which is not possible. So there is no potential drop across R. Out of whatever we apply at V in, nothing will drop across R. All of it will come to X. V in will be equal to Vx. But Vx is exactly what V out is. Output will be equal to input. Let's take the third case where input is positive. Input is positive and we are giving it to the negative terminal. So the op-amp makes the output negative. Diode will get positive potential here and negative potential here. It will be switched on. The circuit can be modeled like this. I replaced the diode with a 0.7 volt cell. Now comes the real problem. The op-amp wants virtual ground condition to be satisfied. It wants the potential at X to be equal to 0. This is what the op-amp does. Op-amp will give negative 0.7 volt at Y. All of that will be dropped across the diode. And the potential at X becomes 0. There is another way to look at it. Op-amp gives negative 0.7 so that the diode is on, so that current can flow through the resistor R. How much current? Enough so that the potential across R, which will be IR, will be equal to the input, which means all of input will drop across R and potential at X will be equal to 0. If you remember, in the earlier case, no current was flowing through R, so no potential dropped across R. All of V in came at X. But now it won't happen. Op-amp will make sure that current will flow through R, such that all of input will drop across R and potential at X will become 0. Let's write this down. Op-amp decreases Vy so that current flows through R, and V out, which is equal to Vx, becomes equal to 0. Virtual ground condition is satisfied. So we got V out, which is Vx, is equal to 0. And Vy is negative 0.7 volt. So this is all we have. When input is 0, output is 0, Vy is negative 0.7 volt. When input is negative, output is input, Vy is plus saturation voltage. When V in is positive, V out is 0, Vy is negative 0.7 volt. Let's take a sinusoidal input signal and plot the output. It will look like this. We have all the negative half cycles and none of the positive half cycles. Let us also plot Vy. It will look like this. For negative half cycles, it is negative 0.7 volt. For positive half cycles, it is the upper saturation voltage. Let us now plot the current through the diode. A current will flow through R like this. It cannot go into the terminal, so it will flow through the diode like this. When input is positive, output is 0. That means for the resistor, potential on one end is V in, potential on the other end is 0. The current through it will be V in minus 0 divided by R, or V in by R, which is also the current flowing through the diode. When input is negative, output is equal to input. For the resistor, it has V in potential here and V in potential here. Current through it is 0, which is also the current through the diode, so it is 0. If we plot the graph, this is how it will look like. Now, what if I want an inverting precision rectifier that rectifies all the negative half cycles and keeps the positive ones? All we have to do is switch the direction of the diode. The circuit will look like this. Let's take the first case where input is 0. The Opamp will try its best so that the virtual ground condition is satisfied. For that, the feedback loop is needed. For that, the diode has to be switched on. So Opamp will make Vy plus 0.7 volt so that the diode will be barely on, start conducting current which flows through R, will make sure all of V in drops across R and Vx is 0. Or we can say Vy is 0.7, all of it will be dropped across the diode and Vx will be 0. Output is the same as Vx. So here output will be 0, Vy is 0.7 volt. In the second case, input is less than 0. Again, the same thing will happen. Opamp will give plus 0.7 volt over here. So all of that will be dropped across the diode. And over here we get 0. So that virtual ground condition is satisfied. Another way to look at it is like this. V in from 0 becomes more negative. Vx still has to be 0. So what changes? Current through R changes. More current will flow through R so that IR is still equal to the higher negative input voltage. All of V in will drop across R and Vx becomes equal to 0. And the Opamp is happy because virtual ground condition is satisfied. Here again, V output is the potential at X. V output will be 0. Vy, as we saw, will be 0.7 volt. Let's take the third case, input is positive. This is the simplest because when input is positive, the diode gets positive potential here, it will be switched off. Feedback loop will be broken. Without feedback loop, no current will flow through R. That means no potential will drop across R. All of V in will reach X. So V out will be equal to V input. Again, we are getting a positive potential at the inverting terminal. Since there is no feedback loop, effective gain is the original infinite gain. Output will be negative infinity multiplied by some positive input. This will give us a negative saturation voltage at Y. Vy is minus Vsat. Let's take a sinusoidal input signal and plot the output. It will look like this. We have all the positive half cycles and none of the negative half cycles. Let's also plot Vy. It is 0.7 when V input is 0 or negative, and it is negative Vsat when V input is positive. The graph will look like this. Let us now plot the current through the diode. Current flows from the P side to the N side, so it will flow in this direction and then it will flow through the resistor R. When input is positive, output is 0. That means the potential at this point is 0. Current through R will be 0 minus input divided by R, which is also equal to the diode current. So we get negative V in by R. When input is negative, output is equal to input. Resistor will have equal potential on both ends. So current will be 0. If we plot it, this is how it will look like. Till now, we have only discussed half-wave rectifiers. What if I want a precision full-wave rectifier? A full-wave rectifier that rectifies even very small signals. We will need two op-amps for that. The circuit will look like this. We will analyze it and see how it works the way we want. But before that, the first rule of analyzing any circuit according to the legend is do not panic because circuits don't bite. Let us start with the negative half cycle. Input is negative. We are giving a negative potential to the inverting terminal. So at the output we have positive potential. D1 will get positive potential to the N side and negative potential on the P side. D1 will be switched off. D2 gets positive potential on the P side and negative on the N side. So D2 will be on. We can model the circuit like this. I replaced D1 with an open circuit. I replaced D2 with a 0.7 volt cell. Let's call this point Y and the potential there Vy. Now, let us say the potential over here is V. Then the potential here will be V. That means the potential at this point is V. Since the op-amp will satisfy virtual ground condition, potential here will be V and hence potential here will also be V. For the first op-amp, non-inverting terminal is at ground. Satisfying the virtual ground condition, potential here will also be 0. Now let us call this point A and apply Kirchhoff's current law there. What are the currents we have? Through this resistor, a current will flow. Another current will flow through this resistor and eventually through this resistor. How about this one? Will there be a current? Assume there is a current flowing through this resistor R. Maybe it flows like this. Then it reaches a junction over here. It cannot flow like this because then it will have to go into the input terminal, which is not possible. It also cannot flow like this. Why? If it has to flow in that direction, that means it has to flow from the N side of the diode to the P side, which is not possible. Basically, if there is a current flowing through R, it doesn't have a path to flow through, which means there is no current. There are only two currents at the node A. One is the current through R, which is V in minus VA divided by R. But VA is 0 volt. So that current is V in minus 0 divided by R. Now this current will entirely flow in this direction. Why? Because it cannot flow through R. Now, what will be the current flowing through R plus R? R plus R or 2R has a potential 0 on one end and V on the other end. So this current that flows through the 2R is basically 0 volt minus V divided by 2R. And these two currents should be equal. Current through R is equal to current through 2R. Solving this equation, we can write V is basically negative 2 by 3 times Vi. Now the hard part is over. Let's take the second op-amp A2. It has a negative feedback loop through R. From here, it has an R. It has another R. Together they make 2R. And it goes to 0 volt, which is ground. I'll show it over here like this. At the non-inverting terminal, it has a potential V. But V is negative 2 by 3 Vi. I'll show it over here. These are all the connections that the second op-amp has, right? You can see that this is clearly nothing but a simple non-inverting amplifier. It has a feedback loop of R and 2R. Input is negative 2 by 3 Vi. Output is what we have to find out. It's pretty simple. Output will be gain of the non-inverting amplifier multiplied by the input. Here the gain will be 1 plus R divided by 2R. We have to multiply the input with it. R and R gets cancelled. This becomes 3 by 2. 3 by 2 and 2 by 3 gets cancelled and output is negative of input. Don't we also have to explain how the diode having a knee voltage of 0.7 will not affect any of this? That's like the whole point of having a precision rectifier. Well, it is quite simple. The op-amp will adjust the potential at Vy such that the potential V that we get over here, which comes over here, which comes over here, which comes over here, which eventually comes over here, making a current flow through the two R's, which eventually flows through the R over here, is such that IR becomes equal to V in, so that all of V in drops across the resistor R, so that at point A we get 0 volt, satisfying the virtual ground condition. Now let us consider the positive half cycle. Input is positive. The inverting terminal gets a positive input, so the output will be negative. D1 gets negative here and positive here. It will be switched on. D2 gets negative here and positive here. It will be switched off. The circuit can be remodeled like this. D2 is replaced by an open circuit. D1 is replaced by a 0.7 volt cell. Let's call this point Y. Now the op-amp will give Y a potential, so that the potential we get over here, which will make some current flow through R, which will eventually flow through R, will be such that IR will be equal to V input, so that all of input drops across the resistor R, which means at this point we get 0, and that will satisfy virtual ground condition. Let's call the potential at this point V. Let's call this point A and apply KCL there. How many currents do we have at node A? One obviously will be the current flowing through R. Another one will be the current flowing through this R. How about a third current through this R? It is not possible, because then this current will have to go into the input terminal of the second op-amp, which is not possible. So there are only two currents. One is flowing through R. Let's take its direction this way. Then that current will be V in minus 0 divided by R. This should be entirely flowing through this R, which has 0 potential here and V potential here. So the current will be 0 minus V divided by R. Solving this, we get V is nothing but negative of V input. Now take the second op-amp. It has a feedback resistor R. Here we have another resistor R. On the other end of R, we have a potential V, but V is negative Vi. Let us show it here. At the non-inverting terminal, it has R, which goes to 0 potential or the ground. Why make it complicated? Let us simply show it like this. What you have now is a simple inverting amplifier. Input is negative Vi. So output will be negative V in multiplied by the gain, which is negative of RF divided by R. That gives us plus V in. For positive half cycle, output is equal to input. So for positive half cycle, output is equal to input. For negative half cycle, output is equal to negative of input. If we take a sinusoidal input and plot the output, this is how it will look like. Clearly, we have a full wave rectifier. And even when we use a practical diode with a non-zero cut-in voltage, it will not affect our output. So that's all about it for today. See you in the next video. And please don't forget to subscribe.